All right, today we're going to dive into a really fascinating research paper, and it asks a huge question. What if we could finally solve a whole class of math problems that for the longest time people just thought were, well, unsolvable? And look, these aren't just some abstract equations on a chalkboard. We're talking about the very engine that powers some of the most advanced AI out there today.
So here's how we're going to break it all down. First up, we'll get a handle on the game we're trying to win, the minimax problem itself. Then we'll explore the treacherous landscape that makes this game so ridiculously hard. But the real excitement kicks in when we get to the clever trick these researchers used to basically simplify that landscape. That trick is what let them build a brand new algorithm, which we'll look at next. After that, we'll dig into the proof that guarantees it actually works, and to wrap it all up, we'll see how this connects back to the real-world tech it's about to totally revolutionize.
Okay, let's get right into it. Section 1, the minimax game. Before we start talking about super complex AI, it's really helpful to remember that, at its heart, this whole problem is just about a competitive game of strategy.
Yeah, it's a great question, right? You might not think a board game has much in common with training a sophisticated AI, but honestly, the strategic core is exactly the same. Think about it. Whether you're trying to anticipate your opponent's next move in chess, or you're training one AI to generate a realistic image while another AI is trying to spot the fakes, you are dealing with the very same dynamic. That dynamic? It's a minimax problem.
So imagine you're playing a game. Your entire goal is to keep your opponent's score as low as possible. But here's the thing. You know that your opponent is, at the exact same time, trying to make their score as high as possible. So to win, you can't just make a good move. You have to make the best possible move, assuming your opponent is also going to make their best move. The solution then isn't the absolute lowest point or the absolute highest point. It's this stable balance point, what they call a saddle point, where neither you nor your opponent can get a better outcome just by changing your own strategy. That sounds pretty straightforward, doesn't it? Just find the equilibrium. But, if it were that easy, this paper wouldn't be such a breakthrough. See, in the world of advanced AI, this game isn't being played on some simple flat board. It's being played on an unbelievably complex landscape. Let's take a look at these challenges.
The playing field for these kinds of problems isn't like a smooth, predictable bowl where you can just roll a ball and know it'll end up at the bottom. The paper calls it nonconvex, nonconcave, and constrained. A much better way to picture it is to think of a rugged, sprawling mountain range. It's just full of these deceptive peaks and valleys, and to make things even tougher, you're not allowed to just wander anywhere you want. There are really strict boundaries you have to stay inside of.
Okay, so this slide really breaks it all down for us. Let's start with player 1, the minimizer. Their whole goal? Find the absolute lowest valley on the map. But here's the catch. The landscape is non-convex. What does that mean? It means it's absolutely littered with these little local dips, these false bottoms that can easily trick you into thinking you've found the real solution when you haven't. Now, at the same time, you've got player 2, the maximizer. They're facing a non-concave landscape, which is kind of the opposite problem. It's full of all these tempting little peaks that aren't the actual highest point. And as if that's not hard enough, both players have to follow strict rules, constraints, that tell them where they're even allowed to look. It's this constant push and pull, this tension, that makes the whole thing so incredibly challenging.
So here's the crucial takeaway. Navigating this crazy, constrained landscape to find that one single true saddle point is just incredibly difficult. And for this specific class of problems, researchers just didn't have a method that was both guaranteed to work and be efficient. You might find an answer, sure, but you could never be certain it was the right one, or it might take a ridiculously long time to find it.
So, how on earth do you solve a game that's this hard? Well, this is where it gets really cool. The researchers behind this paper didn't just find a better way to play the game, they found a way to actually change the game itself. Let's look at this game-changing trick.
Just think about it for a second. If you're totally lost in some rugged mountain range, what's the single best thing you could do? Probably get to a higher vantage point, right? So you can see the whole landscape more clearly. Well, that's the exact same intuition behind this breakthrough.
The technical name for this new perspective is the lifted minimax problem. I know it sounds kind of complicated, but the idea itself is actually beautiful and elegant.
So, this lifted problem is mathematically identical to the original one. The solution is in the exact same spot, but by cleverly rewriting the equations, they essentially smooth out the landscape. It makes all those distracting local peaks and valleys way less prominent, so an algorithm is much less likely to get stuck in one of them. It's like you're going to the same destination, but now you have a much clearer, more direct path to get there.
Okay, so with this new, much clearer view of the landscape, the researchers could finally design the thing that was missing all along, a reliable set of rules, an algorithm, to just march straight towards the solution. The algorithm they came up with is called an inexact proximal gradient method. I know, that's a total mouthful, but you can just think of it as a smart step method. It uses this clever process called sequential convex programming as a little helper, a subroutine, to figure out where to go. And the whole thing turns into this two-step dance between the two players, and they just methodically close in on the solution. So here's how it works. First, starting from wherever the minimizer currently is, the algorithm figures out the absolute best possible move for the maximizer. That's what they call the inner problem. Then, using that new information, it calculates a smart, updated move for the minimizer. That's the outer step. And then, you just do it again. You repeat this dance back and forth. And with every single iteration, they get closer and closer to that perfect equilibrium point. Now, for this whole process to actually work, you need some kind of guarantee that you're making progress and not just, wandering around in circles on the landscape. And that guarantee comes from a mathematical property with a crazy long name, the Kurdyka-Ło condition, or just the KL condition for short. Honestly, the best way to think about this KL condition is as a guarantee that's just built into the map of the landscape. It basically promises that if you start walking downhill, you are guaranteed to eventually reach the bottom of a valley. You're not going to get stuck on some weird flat plateau forever. This property is what ensures that the step-by-step dance of the algorithm is always moving towards a solution, and that it will eventually converge. So, we've got a clever new perspective and a really smart algorithm. But in the world of math and computer science, that's not enough. You have to prove it. You need that formal mathematical seal of approval. And really, the biggest question is always about efficiency. It's one thing to have an algorithm that will find the answer, eventually, but it's a whole other ballgame to have one that will find it in a reasonable, predictable amount of time. So the researchers needed to provide something called a complexity guarantee. Okay, I know this formula on the slide looks super intimidating, but let's just demystify it really quick. This is the complexity guarantee. Basically, that little epsilon symbol represents how close you want to get to the perfect answer. And this formula tells you exactly how many steps or iterations the algorithm needs to take to get that close. It's like the mathematical receipt that proves this method is predictably fast. For the very first time, we have a concrete performance guarantee. It turns what used to be total guesswork into a real science. And that's really the bottom line here. What this research gives us is the first ever method that provides a provably efficient and reliable way to find the solution for this whole class of constraint, non-convex, non-concave minimax problems. It's a massive step forward. So why should we care about all this complex math? Really, why does it matter? Because this isn't just some theoretical exercise. This breakthrough has real, tangible, real-world applications that actually affect the technology that you and I use every single day. Yeah, this breakthrough has an immediate and huge impact. For something called adversarial training, it means we can build AI for things like self-driving cars that are much harder to fool with, say, confusing road signs. For generative adversarial networks, or GANs, it means more stable training, which leads to even more realistic AI-generated art and video. It improves reinforcement learning for training robots to do really complex tasks, and its reach goes way beyond AI, into fields like economics and engineering. So this isn't just one niche solution. It's a foundational tool with an incredibly broad impact.
So at the end of the day, what this research really gives us is a reliable map and a compass for a type of terrain we used to think was almost impossible to navigate. It solved a whole class of problems once thought to be totally out of reach for any efficient method. And that just leaves us with a really fascinating final thought. Now that we have this new tool in hand, what other seemingly unsolvable problems are now suddenly within our grasp?
Have you ever stopped to think about how you'd teach an AI to make the best possible choice when everything's stacked against it? When the world isn't just complicated, but it's actively trying to trip you up? Well, let's dive into that, because some researchers have just dropped a brand new playbook for solving exactly these kinds of what you'd think are impossible problems. So this is really the heart of the question we're going to tackle. How do you program something to win a game, where the rules are super complex, the board is always changing, and your opponent has one single goal, to make you fail spectacularly? This isn't just some abstract puzzle. It's honestly one of the biggest hurdles in artificial intelligence right now. All right, so to really wrap our heads around this, first we've got to understand the kind of game we're talking about. Forget chess or checkers. This is a game that's played out in the real world. And believe me, the stakes are a whole lot higher. Let's use an analogy that we can stick with for this whole explainer, okay? Picture a self-driving car. For that car's AI, every single second it's on the road is like a high-stakes adversarial game. Its main goal? Get you to your destination in one piece. But then you've got other drivers, sudden downpours, pedestrians who just jump out. All of these are potential adversaries, turning a simple drive into something kinda chaotic and dangerous.
So this is what folks in AI and mathematics call a minimax problem. And the name pretty much says it all, right? You're trying to minimize your maximum possible loss. The car's AI isn't just trying to find a good path, it's trying to find the absolute best path. And it's doing it while assuming that at any second, another driver might make the single worst, most dangerous move possible. It's basically a strategy built on pure, calculated pessimism.
Now here's what's so wild, and what this slide shows so well. It's the huge leap in difficulty. A simple optimization problem, that's like finding the very bottom of a nice, smooth valley. No big deal. But a minimax problem? Oh, that's like trying to find the safest, lowest pass through a jagged mountain range, all while some opponent, your maximizer, is actively trying to push you off a cliff toward the most dangerous peak they can find. The world isn't just sitting there, it's actively fighting back against you. Okay, so we've got it. This is a tough, adversarial game. But here's the thing. Solving minimax problems isn't a totally new idea. The real game changer in the research we're looking at today comes from adding another layer of complexity, one that's brutally realistic. You see, most of the older methods for cracking these mini-max problems kind of treated the world like a big open field with no boundaries. But that's not how reality works, is it? Our self-driving car isn't off-roading in an empty desert. It's driving on a highway in a city where there are rules you just can't break. And this right here is the absolute key. The paper introduces what it calls constraints. For our car, these are literally the rules of the road. You can't break the speed limit, you can't drive up on the sidewalk, you physically cannot turn the wheels sharper than the car is built to handle. These are not suggestions, they are hard and fast limits that any solution has to obey. In the math of the paper, you'll see this little bit of notation. C of y is less than or equal to 0. All that means is that the rules function, the C, can't be broken. It has to be 0 or less. Now, adding these rules might sound like just another little detail, but it's not. It makes the whole problem insanely harder to solve. I mean, exponentially harder. Now, our AI doesn't just have to find the safest mountain pass. It has to do it while staying perfectly on this tiny, winding trail, and it can never, ever step off the edge. A lot of the old playbooks for that open field problem, they just fall apart here. And hey, don't just take my word for it. The researchers themselves, Zhaosong and Xiangyuan Wang, they say it right in their introduction. Before they came along, there just wasn't a solid, reliable way to solve these super complex mini-max problems with all these real-world rules attached. They were basically drawing the map for a whole new territory. So, how'd they do it? How do you even begin to create a strategy to navigate this dangerous, rule-filled world? Well, they came up with this really brilliant, almost elegant 3-step playbook. Let's break it down.
Okay, this slide is really the whole shebang. Step 1, lift and simplify. This is so clever. Imagine you have a tangled up shoelace on a table. It's just a mess. But what happens if you lift it up into the air into a higher dimension? All of a sudden, you can see it from all sides and it's way easier to untangle. That's pretty much what this step does with the math. By moving the problem into a new space, those complicated rules suddenly become way easier to handle. Then, step 2, solve sequentially. Trying to map that whole scary mountain range at once is a non-starter. So instead, the algorithm breaks it down into a series of small, easy-to-manage hills. Each one of these is a convex problem, which is just a technical way of saying it's shaped like a simple bowl. It's got only one bottom, and if you drop a marble in it, it's always going to roll to that single lowest point. They solve one hill, then the next, and so on. And finally, step 3. Approximate and update. The algorithm doesn't even need a perfect answer for each little hill. It's all about finding a good enough direction, taking a small step, then reevaluating and updating the big picture strategy. It's this awesome iterative cycle.
But wait, how do we know this whole process won't just get stuck in a little ditch somewhere and never find the real answer? Or just go in circles forever? That is where this very fancy-sounding concept comes in, the Kurdyka-Ło condition, or KL for short. This is the secret sauce.
It's a fundamental mathematical property of the problem's landscape that basically acts as a guarantee. It ensures that every single step the algorithm takes, no matter how tiny, is a step in the right direction. It promises that the process will eventually land on a stable, correct solution and not just wander around lost in the mountains. So we have this really powerful new playbook based on some pretty advanced theory. But what does it actually mean for us in the real world? Why should we care about solving this abstract math problem? Let's check out the applications. The impact here is actually huge, and it's all over the place. Think about generative AI. You don't just want it to spit out an image. You want an image that follows certain rules, right? Like draw a person with 5 fingers on each hand. That's a constrained problem. Or think about training a factory robot. It needs to do its job fast, that's the men part, while avoiding any people who walk by, the max part, and staying inside its physical safety cage. Those are the constraints. This stuff also applies to making better economic models, and this one is huge in cybersecurity, building defenses that can predict a hacker's worst attack, all while staying within the system's own rules. And look, this proves that this whole thing isn't just theory. It actually works, and it works incredibly well. The researchers tested it on a really tough problem. On this slide, you're seeing a simplified version of their results from Table 1. The objective value, you can just think of that as the danger score, it started out at 1.42. But after they ran their new algorithm, that score dropped all the way to -579. I mean, that is just a mind-blowing improvement. It's not just a little bit better, it's a completely different, fundamentally safer and more optimal solution. The algorithm didn't just find a path through the mountains, it found a superhighway. It's proof that this playbook is the real deal.
So, we've seen the problem, we've unpacked the playbook, and we've got the proof that it works. So where does that leave us? What's the really big takeaway from all of this?
The most important thing to get is this. We've basically unlocked a whole new capability for AI. You see, the classic problem was that for an AI, the smartest move to win often meant breaking a rule. And if you force it to follow the rules, it might not be able to make that winning move. This new framework is the first of its kind that can find that perfect sweet spot, the solution that's both brilliant and rule-abiding. It's all about building AI that isn't just clever, but is also safe and reliable from the ground up, because its intelligence works inside boundaries it can't cross. And that brings us to one last really exciting question. Now that we can actually solve these incredibly complex, rule-bound adversarial problems, what's next? What's the next challenge that today we think is completely unsolvable, but tomorrow might be just another problem we have a playbook for? This research doesn't just give us an answer, it really just opens the door to a whole new world of questions.
Have you ever wondered how an AI can learn to beat a chess grandmaster, or how a self-driving car seems to anticipate what other drivers are going to do? Well, it often boils down to solving a very special kind of strategic game. Today, we're diving deep into a problem that's right at the edge of this field, a problem that honestly was considered unsolvable until very recently. We're going to break down a paper by Zhaosong and Xiangyuan Wang that offers a truly brilliant new way to tackle this challenge. So let's jump in. Okay, so at the very heart of all this is something called the minimax problem. The easiest way to think about it is like a constant tug of war. You've got one player, the minimizer, who is pulling with all their might to make a certain number as small as possible. And at the exact same time, you've got the maximizer, pulling on the other end, trying to make that exact same number as big as possible. It's this constant tension, this perfect opposition that's at the core of so many problems in AI.
All right, here's our game plan for today. First, we'll really get into that tug-of-war idea. Then we're going to see how things get way, way harder when you add a wall of constraints. After that, we'll get to the really cool part, the author's ingenious solution, what they call a clever lift. We'll look at the actual tools they built for the job, and, finally, the proof that this whole thing actually works and has a guaranteed finish line.
So, let's get into it. A simple tug-of-war is one thing, but the problem this paper tackles is on a whole different level of complexity. We are not playing on a flat, even field here.
You know, a lot of standard machine learning problems are kind of like trying to find the lowest point in a nice, smooth valley. There's one bottom, and your goal is just to get there. But the problems we're dealing with today are what's called nonconvex, nonconcave. Now, what that really means is that the landscape is a complete mess for both players. For the minimizer, it's not one smooth valley, it's a whole mountain range with tons of different valleys. And for the maximizer, there are tons of different peaks. It's a bumpy, chaotic, and totally unpredictable landscape.
Okay, so as if that bumpy landscape wasn't hard enough, the researchers decided to add another massive layer of difficulty. What if one of the players can't even move freely? What if they're trapped? And this slide just lays out the challenge perfectly. In a simple minimax problem, it's an open field. Both players can go wherever they want. But in the problem this paper solves, the maximizer is literally boxed in. They have to play by a super strict set of rules, which means they're trying to win this tug of war while also navigating a complex maze at the same time. It's just so much harder. And this is the absolute key. Before this research came along, nobody had an algorithm that was guaranteed to solve this specific kind of problem, the bumpy landscape with one player stuck in a maze, in an efficient way. It was a huge, huge roadblock for a lot of important areas in AI.
So this brings us to the author's central idea. And frankly, it's just brilliant. They realized that instead of trying to build a better vehicle to get through the maze, they should just redraw the entire map.
So think about it. How do you even begin to approach a problem that has stumped an entire field? A problem where there's just no known efficient solution?
Well, you don't just keep banging your head against the same wall. You get clever. You find a way to transform the problem itself into an equivalent version that's actually much, much easier to deal with. And this is what they call the lifted minimax problem. It is such a cool idea. The authors essentially lifted the problem into a higher dimensional space by adding new variables. Here's an analogy. Imagine you're stuck in a maze drawn on a 2D piece of paper. What if you could suddenly jump into 3D, fly right over the walls, and land at the exit? By adding that new dimension, you've made the maze trivial. That's kind of what they did here. The destination is the same, but the path to get there becomes unbelievably clearer.
But, of course, for this brand new map to be useful, you need some kind of guarantee that it's actually, navigable. And that is where a very important piece of math comes in, something called the local Kurdyka-Ło condition. Let's just call it the KL condition. This is the secret sauce that makes the whole thing work.
So what on earth is this KL condition? Don't worry, it sounds way more complicated than it is. Imagine you're walking around a hilly area in the pitch dark. The KL condition is basically a promise that you'll never find yourself on a perfectly flat spot where you have no idea which way is up or down. There is always a downward slope somewhere nearby. And that property is absolutely crucial because it guarantees that an algorithm can always find a direction to move and won't just get stuck forever. Okay, so we have our new, better map, and we have a guarantee that we won't get stuck on it. The next logical question is, what tools do we actually use to make the journey? And that brings us to the algorithm itself. So here's the play-by-play. It's really like a little dance between the two players. In step 1, they focus on the maximizer, the one stuck in the maze. They use a special technique to find a pretty good, though not perfect, next move for them. Then, in step 2, based on where the maximizer is going, the minimizer takes a small, intelligent step in their own best interest. In step 3, you just repeat that dance, over and over and over, and that steady back and forth gradually guides both of them to a stable solution where neither one can do any better. All right, so we've got the new map, we've got the new toolkit, but the million-dollar question is, does it actually work? Does it lead anywhere? Well, the authors put it to the test. And let me tell you, the results were not subtle. They were dramatic. They ran their algorithm on a really complex problem that was specifically designed to have all these nasty features we've been talking about. Just take a look at these numbers. The objective value, that's the thing the minimizer is trying to crush, it started out at a positive 1.42. After running their algorithm, it plummeted all the way down to nearly negative 580. I mean, that's not just a small improvement, that is a fundamental shift, proving that this algorithm is incredibly good at finding its way down into a really deep valley on this crazy landscape. And get this, it achieved that massive improvement in just 2,500 iterations. Now that might sound like a lot, but in the world of complex optimization, that is lightning fast. It proves the approach isn't just a cool theory, it's actually practical. But here is the single most important part of this whole story. The numerical result is awesome, don't get me wrong. But the real, honest-to-goodness breakthrough of this paper is the mathematical proof. They didn't just show that their algorithm worked on one test case. They proved that it is guaranteed to work efficiently for this entire class of previously unsolvable problems. So let's zoom out. What's the big picture here? Why does this one problem matter so much? Well, because this is the very first method that comes with that mathematical guarantee of efficiency for this entire class of problems. It opens the door to creating AI that is way more robust and reliable. Think about training AI for cybersecurity, where you're in a constant battle with adversaries. This work provides a new, provably effective toolkit that could lead to much, much more secure systems. So if you take away just one thing, let it be this. Liu and Wang have taken a problem that was basically an open frontier with no reliable maps, and they didn't just provide a path. They provided a mathematical guarantee that the path leads to a solution, and then it gets you there fast.
It really makes you think, doesn't it? So much of this cutting-edge research is about figuring out how to navigate these seemingly impossible landscapes. What this paper shows is that sometimes the most powerful tool isn't just a stronger engine, but a better map. And it leaves us with this really exciting question. What other impossible mountains in AI are out there, just waiting for someone to come along and redraw the map, turning them into walkable hills?